So welcome to this tutorial of the magmaOffenburg team. With me is Hannes Braun, who will take some of the parts. And my name is Klaus Dora. I'm team leader of magmaOffenburg. Okay, so let's start. Maybe we can go quickly on this one because those I see have already some experience with RoboCup. RoboCup is an initiative to get, by the year 2050, develop a fully autonomous team of humanoid robots who can win against the human world champion. And this is an initiative since 1997, and the magmaOffenburg team has participated in world championships since 2009. Graz was our first world championship, and since then we have been part of this endeavor. Over the years we improved step by step. And since 2017, we are 3 times runner-up in the World Championship and have been winning the Robotica and also the Brazil Open last year. This is a team picture. Of course, it makes a lot of fun to participate in RoboCup events, and that's why we want to share this fun with you. So we shared our code with you, a big punch of our code, and this is what Hannes and I will show you and explain. So starting with this, Hannes will explain step by step how to get our code, how to open it in Eclipse.
So we will start by doing this in Eclipse. First up, we're going to create a new workspace for Eclipse. We will launch Eclipse. We're closing the welcome screen, and we're choosing it's perspective. I'm sorry, open perspective, other, and choose Git. Click open, and now we want to clone a Git repository, which is our GitHub Magma release repository. So the URL is https://github.com/magma release.git, and click next. We want to select the main branch. Next, and click finish. So the defaults are no, we have to no, click finish. Okay, so after that is done, you'll see the Magma release repository here with the commits we already did. Now you go back to the Java view and click on import projects, and now search for Maven and choose existing Maven projects. Import, select existing Maven projects, click next, and it got cloned here. Here's our Magma release repository. Click on open and make sure that every project is selected here, and then click finish. So now it's importing the Maven project, and you'll see all the packages that we defined here. Now it's easier to actually use the project explorer. So click on window, show view, and choose project explorer. Now you can close the package explorer since you probably don't need that anymore. Also, it's a lot easier to see the Java packages in a hierarchical view. So choose these 3 dots, go to package presentation, and choose hierarchical. Now you can see here our project. This Magma is the main project, and we've got different sub-projects, which Klaus is going to tell you about later. Now, for the first step, you may want to actually just start a team. So you go to this run button here and click on the little triangle and go to run configurations. And underneath Java application, if you expand this section, you'll find the RoboCup client. And you can run this. In the background, I already started the simulation server and RoboViz. So if I now click run and go to RoboViz, you'll see that we now spawned our player. And now we can kick off, and it works. To make it stop, you may want to add the console view here. So click on Window, Show View, and add the console view, and we can stop the agent again. So that's the basic setup for Eclipse. Now just for IntelliJ again, it's basically the same with some tweaks. So I'm going to clone it this time from the command line. So you've also seen this. I'm just going to make a new directory called IntelliJ. And I'm going to clone the repository again. Okay, so now that it's cloned, we can go back here, minimize Eclipse, and open up IntelliJ. And we'll open up the project. So this should be located here. Yeah, I got it right this time. Open up the repository that we cloned. We want to trust the project. So you'll find a lot of this information that I just told you also in the README. If you want to read again what I said, for now this is fine. So to actually just start the player again, you can add a configuration. Just plus back here and choose application. Name it something like RoboCup client. We need to specify a module. I'm choosing my JDK 8. The class path is Magma agent. And the main class is magma.robots.RoboCup client. And for the program arguments, you want this to be maybe the player ID 8, which is also the default in the Eclipse run configuration. We want to see robo with debug information if they are available. And maybe we also want to, we want to use the now toe as the robot. So we specify factory now toe. And we'll hit OK. And again, if I run this, the player should appear here. So it's building right now. We have to wait a few moments. Okay. Okay, it's spawned in the back because I already started the game, but you can see that it works. So that's the basic IDE setup. Maybe it's also important to note that we included a Maven wrapper. So go to the repository. And maybe you don't have Maven installed yet, so that's no problem. You can use the Maven wrapper. And to build the whole project, and which you probably need to submit a team binary at some point to specify the go clean and then package. Oh. Now it says permission denied. Maybe the Maven wrapper is not executable on your system, so just make it executable by executing change mod plus X and may W, and now this command should run fine. Now when this is done, we'll have a directory which is ready to submit maybe for a competition, which will also include some start scripts, which will start the whole team. So you will find this inside the directory Magma agent, which is the main or most important module maybe from the project. And in the target directory underneath Magma agent, you'll find all the artifacts that got produced now. So there are different start scripts. The most important ones are start.sh and kill.sh, which are used to start the team. And inside the lib folder, you'll find all the jar files from the project, as well as the dependencies. So if I type ls-lib, you'll see there we have our magmaagent jar, and also some dependencies like commonsmath from Apache. And now I could just dash start.sh localhost, which would start a team on my local machine. But that's now the point where Klaus is going to take over again, because my server is a bit too weak for that.
Here we are now in this folder that was created by Maven, target magmaagent. This is the deployment. So if you copy this magmaagent folder to the competition server, then your team will be available. And one thing we do before starting a team, we will check if the team name is okay. So this is what you can do inside the start script. You specify a team name. That seems to be okay. So what we need now is two things. We need a simulation server. This is what Marco and the others have told you how to set up in the previous tutorials. So with the server running and the RoboViz running showing this server, we are now ready to start a team by simply run a team. So we see the first players are appearing. This will run a whole team now. Now, one thing we have to do now before starting a second team, we have to change the team name when all are started, because depending on the team name, the clients will connect to the simulation server. So let's start a second team, and it will be team red here. With team name team 2. And as you can see, our release is providing all code necessary that you can immediately start playing games. The quality of the gameplay is, of course, a bit reduced to our real team, but this is a very quick entry step now to the into the competition. This is how a game looks like, and we will now have a look in how our code is structured and which pieces you have to take your improvements for this team. It's okay. So once again, we have the package diagram of the top level architecture here. Base is the module which contains all code which is not RoboCup dependent. It's code for autonomous systems in general, and we use it for our RoboCup robots, but also for autonomous driving, for example. So everything you find in base does not have any dependency to RoboCup, and those are the base classes, like the main loop of an agent and things like that. KDOLib is our own library for artificial intelligence algorithms. It contains algorithms for genetic learning, which might be interesting to use for you, but also wrappers for CMAES or for neural networks. Common is a library with RoboCup specific code, which is nevertheless reusable, does not have any dependencies on specific robots or things like that. So all of these are reusable libraries. And the core is the most of the classes, and it's quite a number of classes. I think it's 4,500 classes, so you need to have some structure, is inside magmaagent, which has two sub-packages, agent and robots. Agent is all the code which is independent of a specific robot type. So whenever we program something which is not depending on a specific robot type, it's just humanoid robot, then it's inside agent. And inside robots, we have then the robot specific parts, like things that are specific to the now toe or to a now or to our sweaty robot, which we also are on a real robot. So this is the architecture, and you will find this exactly matching in the Eclipse. Like you have the base, which is this RoboCup independent code. We have common, which is RoboCup dependent, but also not dependent, reusable. KDO Lib, an artificial intelligence library, and Magma Agent. And inside Magma Agent, we have agent and robots. Agent, which is robot type independent, and robots, which are robot type dependent code, which is RoboCup dependent code. On the next layer, which is true, which is the design for both for base and Magma Agent, we look into second and third level architecture. Orange is the second level architecture, blue are the third level architecture classes, packages. Starting here with communication, inside communication you find all the classes which are responsible for talking with the server. So for receiving perception, receiving any kind of messages from the robot, no matter if it's the soccer simulation server in RoboCup 3D or if it's a real robot. And sending actions to the server or to the robot. This is what the communication layer does. And this is probably the most uninteresting one. This is one where you would probably not have to make many changes, so we don't go into detail for this one. Then the second level of architecture is the model level. So whenever we receive a new server sensor message or sensor perception, this will be integrated into the model. And inside the model, we have a couple of sub-packages like the meta packages, world meta and agent meta. They contain prior knowledge. So they contain all we know before the game starts. Like in world meta, all the information is about the soccer field size, where the goals are, how big they are, where the corners are, and so on. And in agent meta, we have all prior knowledge to the robot, like how long are my legs, where is my knee, how can I bend it, everything that we know before the game starts. Then in world model, we have all the information what happens around us, like where is the ball, where are the other players, anything we can perceive from the outside. And in agent model, we have all the runtime information about the state of the robot itself, like how my knee is bent, what my foot pressure sensors are telling me, what's my orientation in 3D, in space, things like that. And the thought model is then a high-level knowledge of what the agent believes is currently true. So things like, where do I intend to pass to, or am I the player who should run to the ball, things like that. So this information is, high-level information is stored in the thought model. And we'll see in a minute how to access this information inside the model layer. What's important is that these arrows mean that this can be dependencies, and if there's no arrow, then there's also no dependency. So our communication layer will have no dependency to the model layer, and the model layer will have no dependency to the decision layer. So when you want, you can only take the communication layer and reuse that and put your own team onto that. Or you could say we use the model layer and the communication layer and create our own decision layer. So there are no dependencies from these lower layers to the upper layers, so it's very easy to reuse them. In the decision layer, we have the decision makers, which take the high-level decisions and all the behaviors like walking, kicking, getting up, and so on. Finally, the agent runtime is keeping all these parts together and contains the main agent loop. And again, when we switch to Eclipse, this is how things really look like. So when we are in agent, you will see these layers, the communication layer, the model layer, and the decision layer. And inside the model layer, we have the agent meta, the agent model, the world meta, world model, and thought model. So it's not just on paper, the architecture, it's also really implemented like that. And we are using Arch unit tests to make sure that you don't introduce undesired or illegal dependencies. Unit tests will fail if you make wrong dependencies when changing the code. So As I said, we skipped the communication layer because it's just TCP/IP communication and message parsing and things like that. It's not so important, and it's more interesting to have a look on how now to access this model information. And we have made a couple of simple examples. So whenever you are, for example, in a decision maker, you have access to the thought model by calling get thought model. And then you can simply access all the information which is part of the thought model, like, for example, to get the desired kick position. Content Assist will help you to find what's available there. And of course, it's also easy to add new things to that. So again, thought model, all the high-level information which is interesting, like which is the opponent closest to the ball or things like that. Accessing the world model is accessing information what's happening around us. One thing that you really will like is that on a very low level layer, we make sure that we're always playing from left to right. So you never find in our code any ifs distinguishing if we are playing from left to right or from right to left on the field. We make sure that we always play from left to right. That's already done in the communication layer. That makes things quite easier. If we want to know where's the ball, well, we ask the thought model to tell us the world model, and then we can access the ball and get its position, get its speed, get whatever. Yeah. Or if I want to know where I am on the field, this is a bit special. This is also part of the world model. So inside the world model, we have an instance called this player. This player inherits from players, or has all the properties that all players have, but knows a bit more because this is us ourselves in the world. And from this player, we can also ask for the speed, for the position, but also for the pose. So we know in 2D where we are, but we also know quite well in 3D where we are. We have a localization on field which is 6D. So we know X, Y, and Z coordinates of our torso quite well, and we also know quite well the orientation, all the rotation angles. In the agent model, you will ask things like, where is my foot? How is my foot pressure? What are my arms doing? And here another example of how you can access body parts and body part information. Simply ask for the agent model, and then you can, for example, ask for a specific body part, like all the names are in these human lead constants, and get its pose. So you will get the pose of this body part with respect to the torso in that case. And this is how you can access all the model information. As I said, Content Assist will help you to find what information you find there. It's not simply the ball that you can ask for other players, for own team players, for other team players. Everything is available. The next layer is the decision layer. And what we are using as a decision is a sequential decision maker. So actually quite simple. We have a list of behavior suppliers, and they are checked one by one in this sequence. So first we check if we want to say something, then we check if we want to beam home, and in this order the behavior suppliers are checked. Behavior suppliers like perform say or beam home, they are not using the legs of the robot, so they return null. Whenever a behavior supplier returns null, it means it does not use the legs, so we can do anything else, we can do more. And as soon as the first behavior supplier returns a name of a behavior, like let's assume we are lying on our back and we want to get up, then this get up will return the name of the get up behavior. And that means we don't have to check anymore. This is the behavior we desire to do. One important thing is to know is that this is only the behavior we desire to do. It won't be immediately triggered. Well, get up will be triggered immediately, but for example, moving, for example, to the ball will only be triggered when the current behavior has been finished. So the decision maker returns a desired behavior, but that can be different from the current behavior. Only when a current behavior is finished, we will switch to the desired behavior. There are two classes caring for decision making, the soccer decision maker for the field players, and the goalie decision maker for the goalkeeper. Let's have a quick look. This is how it looks like. And let's have a look, like, how does this look like? These behavior suppliers will check if the condition is met that this behavior should be triggered, like when we find that we are lying on our back or lying on our food, and this is information we get from the world model, from the this player. Then we decide maybe if we try to get back up, then we return the backup behavior, get up from back behavior. If we are lying on the front, we return the get up from front behavior. If we are lying on our side, then we return the move to arm to fall back behavior. And if we are not lying at all, we return null, and then the next decision will be taken. So this is how step by step in the sequence through all these behavior suppliers, the decision is done what to do. And this decision is then hierarchical, like when we go to move, this will return either waiting for the game start, or passive positioning, or active positioning to the ball. And these behaviors will then on their own have a decision maker. So it's a hierarchical decision making. One thing you might also want to change, of course, from the default team is how the team is distributing itself on the field. And this is the class diagram for how we assign roles to the players, and what strategies we use, what formations we use. So there are 3 packages which concern with the high-level role playing of our team. Inside formations, we find how the players are put onto the field in specific situations. Let's have a look. So formations, we would have, for example, the own kickoff formation when we have our kickoff, and for each player, we simply specify where to put this player depending on the name. Easy to change. This is something you will probably want to change early so that your team looks unique. The second thing are the roles. This is, we have a dynamic role assignment that each player takes one of the roles which are available depending on its current play situation. So if a player is a defender, it won't stay forever a defender. If someone else is better suited from positioning to be a defender, then we have a dynamic role switch. How does this look like? So the roles, we have a couple of roles available here. Let's take the defender. You will always have a determined position method, and here you specify where you want to have your defender playing depending on the current situation, like depending on the ball position. And this method will return where our defender wants to be, and it will walk to there if it's not the one player attacking the ball. This is a real role, specifying where the player that takes this role defender wants to position itself. We don't go into details what's the logic now of where to put this player. That's something you can discover on your own. One thing I want to mention is that we have also role decorators, like classes decorating other roles, like for example the man-to-man marker decorator. This is only decorating another role, so you can have a defender which is a man-to-man marker. Yeah. So when there is some opponent in vicinity, then we get close to that one. Otherwise, we will simply behave like a defender. Just from an architecture point of view, so you have roles, and you can decorate these roles with more functionality. This is something you have to take your time to explore a bit. As you can see, we have a couple of roles, and for final, which roles are used is defined in the strategies. So I think currently we play with the react to game state strategy, and this simply defines all the roles we are using and which ones are finally available. So we have a defender, but this defender is then decorated by a man-to-man marker decorator. So our defenders are not just staying in the back, but they try to mark other players. So these are the three components for high-level strategy. We have the formations defining the positions on the field for special cases like kickoffs. We have the roles, which define how a player will finally behave, where a player wants to run to when not running to the ball. And we have the strategies, which will simply provide enough roles that each player gets a role in the end. The only player which is excluded from this is the goalkeeper. The goalkeeper does not take a role, it has its own role, goalkeeper. And that's a fixed role. The next step is to have a look into the behaviors, and here we said we make a bit a slower example, and Hannes will show how we can. We have a couple of different ways to create behaviors to move the robot, and this one is a very common one, so Hannes will make an example of how we can create our first behavior and use a decision maker to show.
This first option to create a behavior are the movement behaviors. Movement behaviors define keyframes in the code to move the player. Well, what does this look like? You can create new movements, give them a name, and you can add new movement phases. So, for example, this is the get ready movement behavior, which I'll show you also in the code in a few moments. So what this does is you're creating a new movement and you're adding a new movement phase. You're calling this movement phase get ready, and the duration of this movement phase is 30 cycles. And for this movement phase, you want to add movements for different joints of the robot. So for example, you're having the right shoulder pitch, which you want to move to the angle minus 50 degrees. And you want to move it with a speed of 3 degrees per cycle. Then you add all the other joints and how to move them. And finally, you got your movement. And for sure, you can also add more movement phases. So yeah, moving joints back and forth and whatever you want to do. So let's actually look at this in the code. You'll find the get ready movement inside the magma agent module, source main Java, magma, and underneath robots. Now and then it's decision and behavior, and this is a movement, and here you'll find the get ready class. And if you open this up, oops, okay, this should now hopefully be big enough to read. You'll see what I just showed you on the presentation. This basically extends the movement behavior. And here you got your create movement function. And you're creating this movement phase. And finally, you're returning the whole movement. Maybe to get a better understanding of what it actually does, let's just create a new movement where the agent moves his arm and tries to wave with his arm. So we will create a new Java class, and let's call it wave arm. And again, make this bigger so you can read it. Now we want to extend the movement behavior again. Okay. Now we're getting an error here that tells us that we need to create a constructor to match the super constructor. So we'll do that. Now it tells us we need to supply a name. Well, it's called wave arm, so we don't need that here. We can specify it here, but actually hard coding it at this place is not a good idea. So we want to open up the iBehavior constants, which defines the names for all the different behaviors we have. So open that up, iBehavior constants. So this is located, just in case you're not using this, underneath Magma agent decision and behavior. And here we got our general behaviors. And now we want to maybe add the behavior name wave arm. So type wave arm and strings also wave arm. Okay, good. Now go back to the movement behavior. Let's actually use the iBehavior constant. So iBehavior constants dot arm. We want to keep the thought model that gets applied. And the initial movement, we're actually creating this inside this wave arm class. So instead of initial movement, we're creating a function called create movement. And we need to create this method first. Okay. And we can now basically do kind of the same thing that we did in get ready. So we'll return a new movement. Which then contain, oh no, we need a name for it. Let's name this wave arm. So this name is actually not related to this as far as I know. You can correct me, Klaus, if this is wrong, but yeah, so we want to add a new movement phase right now. So add, and we're creating a new movement phase. Let's call this phase just simply phase 1. And it has a duration of, say, 30 cycles. And we're going to add some joints to it. So for example, the right shoulder pitch. It's missing.
You have to implement the I now constants.
I'm sure I forgot something. So yeah, implement the I now constants, which will contain those. So this should be available now in theory. Oh. Something definitely is not working right now. Let me check with my pre-made one.
It's I now join, sorry, I was wrong.
Oh, okay. Yeah, now it's available. And so we maybe want to have this the right shoulder pitch at minus 90 degrees and the desired speed at which we want to reach this position of with the joint, say 5 degrees per cycle. We will also want to add the right shoulder yaw. Also minus 90. Oh, I saw there's a typo. This has to be actually 90 degrees. And also with 5 degrees per cycle. And another one, this time it's the right arm yaw. Also 90 degrees with 5 degrees per cycle. And this will create a well, the first movement phase. And before we add the second movement phase, let's actually just make it work so you can actually see what it does right now. So we'll open up our component factory to actually make this behavior available for the agent, because right now this is a class existing on its own, but the agent doesn't know about it. So we'll open up the now component factory, and every behavior that we basically have is added here. So let's actually search for get ready. So the get ready behavior is here in the method create specific behaviors. We're having a list of behaviors, and we're putting the get ready behavior right here into the list. So let's actually also do this for our wave arm behavior. So behaviors, put new wave arm, and supply thought model. Good. Now to actually test this and let the agent decide to execute this behavior, there exists a useful decision maker for that. So that's the training decision maker, and you can use this to just test out a new behavior which will not actually target the ball and kick and do whatever. So you can just use it to test some behaviors. So the training decision maker, if you open that up, it looks like this. So we also use this to test some things. The important part now is the move method. You've already seen the move method previously when Klaus showed you the soccer decision maker. So normally we're doing the attack things here or get ready or whatever. No, get ready. I think we're actually not doing this here, but wherever you can use this to test the wave arm behavior. So here we need to return a string. So what we need to return here is the name of the behavior. So if you remember, we defined that in the iBehavior constants, the wave arm. So we can return that. And now if we're using this training decision maker, we will always just wave our arm instead of doing whatever we specified before. To actually use this training decision maker now, you have to adjust your run configuration. And there's a parameter for that called decision maker. And this decision maker is called training. Oops. Okay. And if we now run our agent, we'll hopefully see. Oh, no, that was my fault. Move that. And again. Okay. Now we're actually seeing the agent here. And now he got his arm up. But we actually want him to move this part or move his arm up and down, so he's kind of waving. So we'll go back to the to this part and add another movement phase. Yeah. So here we're going to add a new movement phase. This time it's called phase 2. With also a length of 30 cycles. And again, we're going to add the required joints. So I'm just going to copy this. And the important part here is the arm yaw, which is now going to be 0 degrees. So if we stop and rerun the agent, you'll now see the agent should appear again, and he's waving his arm. So that's quite cool. And you can do pretty cool things with this. And yeah, that's just a basic method, and I hope this was kind of helpful. Yeah, and I think I'll give it back to Klaus right now.
There we go. So this has been how we create many of our behaviors using keyframes with the movement behavior classes. There is something similar which I only want to mention is the function behaviors. You can define behaviors by defining functions in a file. This is how our win behavior when we cheer. We can use scene functions and sine functions and piecewise linear functions, or also polygons and splines. I don't want to go into much detail here for two reasons. We are not using those a lot, and actually it's only very helpful if you have this function editor. You don't put these numbers manually, but you draw them with the editor. But this is something we have not released. The next kind of behaviors I want to have a look at into more detail is the inverse kinematics behaviors. We have included in our release a complete inverse kinematics solver for the Now robot. And this allows us and allows you now to create behaviors from defining foot positions. And that is what we do for walking, for example. Our walk is an inverse kinematic walk where we specify the way the foot will go. This is from the side. So we lift our foot, we move it forward, we put it into the ground, and we move it backward into the ground a little bit. And this is described in much more detail in our paper from which you see here from 2013. There are two things which are quite nice with this walk engine that you have available now. It's omnidirectional. You can walk into any direction with 3 parameters: walking forward, walking sideward, and turning. And the second thing which is interesting is that it has a balancing engine included. So we have a complete decoupling from the upper part of the robot to the leg part. If the robot is leaning to the side, it will adjust its legs so that it's still able to walk even for 20, 30 degrees leaning to the side, left, right, and also for leaning forward and backward. The robot will compensate for any kind of leaning of the torso. And this I want to show you also in the code a bit, especially the parameters. This will be one place which I suggest also that is one thing when you use our release code to start with the walk parameters. The definition of this curve of how the foot is moving is specified by a couple of parameters like how quick we want to do this. So the release value for this is 14 cycles. We make one step. The walk height will define how far from the ground we have the hip. We have a walk width, which is how far apart from each other the two legs are. And I can show you this maybe while the robot is walking to see what is the difference. And probably learning these parameters to a better parameter set is something you might want to do as a first step to improve the team. So when I start the server and RoboVis, I will start the player. There we go. And let's kick off and put the ball somewhere far so that the robot has to walk a bit. So if we make these steps slower, then the robot will walk with a bit slower steps. It's less stable now, as you can see. We can also make it a bit faster, maybe. Let's wait until it's coming back to us. So this is faster steps now. If we switch back to longer steps, we can change the hip height. So when it's walking a bit higher, not so in the knees, as you can see now. Maybe even a bit higher. that's what you can see also. This is maybe too high. It's no longer able to turn. A bit too high. One nice feature when you use Java for your code is that you have hot code replacement, so that you can change these things at runtime and see how they influence the gameplay. The next thing is the walk width. So how far apart the legs are. Let's walk a bit wider so the legs are more spread apart. We have the walk offset, which is not so important. The max step length, you can make longer steps. Poor robot. So if we have slow steps, we can make longer steps like this, then it will make. And of course, as you can see, that these parameters depend very much on each other. So if we have quicker steps, we cannot make long steps and so on. So now it's making longer steps, and it's also already a bit faster, I would say. Oh, I don't remember the value. What was it? 8? The step width is when it's walking sideward, which it won't do now, only if we are just next to the ball on the side. But the max step height is how much it lifts its legs. Now it's only lifting 2.5 centimeters. Let's say we walk a bit higher. We lift our legs a bit higher on the ground. As you can see now, it's stepping a bit higher. We could do more maybe. And all of this will a good combination of all of these parameters will allow you to walk much faster than the robot does now. Max turn angle is how much we can turn in one step, and actually we could even do more. 50. This is now turning 50 degrees per step. Per step. We could even do more, so we are quite quick with this walk engine to turn. The pushdown factor tells us how much the agent will push its legs into the ground, and so on. So there are a couple of parameters. Those are the most important ones. Maybe I mentioned the others just, and don't change them. How much we accelerate our step length. So when starting to walk, we have to slowly increase the step length. This is what's told with the acceleration. When stopping, it's deceleration. How much we accelerate when turning. We have Zakital and coronal adjustment factors. This is how stiff the robot is, how stiff its neck is when doing when changing its leaning. You can switch on and switch off if the arms are moving. As you can see, it's moving the arms. It's looking better. It doesn't have much effect on the walk. It's a bit more stable, but this is how you can switch on and off. And dynamic walk will switch off the balancing engine. So currently it's walking dynamically, which means if it's out of balance, it will adjust its torso. The last kind of behaviors we have included into our release are so-called full search behaviors. Those are behaviors we learn on joint space with genetic algorithms. As you can see, this is one kicking behavior you see here. I don't want to go into detail what each of these parameters mean. It's for sure that while with the walking engine, you're still maybe able to tune a bit manually. Here with these kick behaviors, the only chance to do is to learn them. And we learn them using genetic learning and CMAES. There's one of these kicks included, so you have already the starting point to learn such behaviors. Also, you have a genetic learning algorithm available in the KDO-lib, and you have a CMAES adapter for the Commons Math CMAES also inside the KDO-lib. So you have all the starting points to do your own genetic learning and learn your own behaviors like this kick walk, which is a very quick kick. The behavior included is, of course, not an optimal behavior. You probably have to improve this and do your own genetic learning on this gene code here. This is what we wanted to show you in our tutorial. And after the tutorial, of course, we have time for questions, whatever you want to ask. Maybe as a final thing, what do we suggest as a starting point to work on? I think the first thing how you can improve the team that we have released is to learn or manually tune the walk behaviors to improve your walk speed. As you might see, our own team is walking much faster. It's using the same walk engine, but using different parameterization, and you can learn or tune this. You probably might also want to create your own team strategy, your own team setup. Where do the players appear on the field? This is something we have shown you. And one thing we are still also on ourselves working on is to improve the goalkeeper. Our goalkeeper is there and is kicking quite well, but it's not catching quite well. And if you are more used to the code and you have more overview on what's happening, then the next step might be to improve the kicking behaviors, like the kick walk that I have shown you. And there you only have a chance to do this with machine learning techniques. It's nowhere that you can go with manual tuning these parameters. You have to use machine learning. The simplest way to start with is to improve current existing kicking behaviors. We have included a kick walk kicking behavior that's kicking straight. This can be improved, certainly. But the next thing you might want to do is then create derivatives from it, like one kicking diagonal, or one kicking backward, or one kicking to the side. This is something where you can learn your own full search behaviors. What we are currently doing, and this is not included yet in the release, is we are using deep reinforcement learning to learn behaviors. And that's, of course, another step you might want to take.